And welcome to Calculus in the AM. I have Calculus in the PM in the afternoon. Calculus AM is in the morning. Welcome to my class. This is concavity and the second derivative test. Remember we had second derivatives, do the derivative, do it again, right? You fry the beans. So let's just think about, remember from yesterday, what does the first derivative tell us? If the slope of the tangent line, so we're not talking about second, if f prime, the first derivative, if this is the function, f prime here on this side is positive, correct? Left to right, it's increasing. And it gradually becomes 0. And yesterday's lesson basically was, if you're looking for maximum or minimum points, you're looking for 0 slope, or what is the other part? Where the slope, as tangent, is undefined. Yeah, where this derivative, first derivative is undefined or 0. But if you look at a maximum, slope is 0 here, but before that it was positive values, and then it switches to negative, right? And it becomes more negative. Now we've seen this, right? Positive switches to negative, and I'm asking you to actually write that statement, and Hashim, you had a little practice before too with that. Okay. If it's a minimum, the first derivative, but I didn't mean to do that, there. The first derivative on a minimum switches from negative values that approach and get to 0 to positive values. So when you switch from positive to negative, that's a maximum. When you switch from negative to positive, that's a minimum when we're talking about first derivatives. Now here's the thing. The derivative of the derivative, what's happening? What's going on there? Well, that's the second derivative is going to explain. So if the first derivative is increasing, it's going from positive to negative, then the second derivative, when you take it and evaluate it at this point, it'll be negative. And it's called concave down. Actually, it'll be negative for all of these. Okay. If the first derivative is increasing, like this, you see, even though it's not the function that's increasing, right? The first derivative is going from negative, 0, positive. The second derivative is positive, and the curve is concave up. Concave up. Hey, works great on a quadratic equation because it's the same thing as before. Second derivative, this works for. If it's negative, second derivative. Concave down. Happy face. Concave up. Now it doesn't have to be a complete smile. It could be a function like this is concave up, but it never actually, on the left hand, it never swerves up. If we were talking like 10 to the power of x or something like that, I'd still consider concave up. But you see how the bowl portion of it is up, even though it's only sort of like the left or the right half. Okay, so a test for concavity. Concavity describes the curviness. If the second derivative is greater than 0, so if it's positive, all you have to remember is happy face, right? If it's negative, sad face, right? Ça va mal. Okay, then, sort of like critical numbers could be doesn't have to be a maximum or minimum on first derivatives. An inflection point is where you switch signs. And you have so you're looking for zeros or the spots where a second derivative doesn't exist. And if it does switch signs, and you're going from concave up to concave down, that's called an inflection point. Similar method to find them. Look for your zeros or spots where it's undefined. So it's found where the second derivative is 0 or doesn't exist. Now here's a spot. If you do the cube root of x and graph it, it looks like this. I want to show you something where it doesn't exist, right? That kind of thing. if you do the derivatives, the inflection point, you should be able to do this by picture, right? Intuitively, as well as algebraically using calculus, okay? You see how that's a inflection point there? Okay. So it doesn't always look like a sine curve kind of thing. Now that's just information. Let's try something else. So for this function, x to the 4 minus 54x squared. Now, although you don't have to graph it, you should intuitively have some ideas of what this function looks like. Now the lead term, the term in front of the highest degree, x, is 1. It's positive 1. And it's an even function, the highest degree. So what does that mean about the way it starts and stops? Yep, I see it. It's probably a W type of thing. Right? At the very least, we know it starts here, something here, some action happens in between. Don't know the details about it, but, right? We know this much. We know that, then that tells us, like I said, I just maybe could be like this, but what are you guaranteed to not have as far as the first derivatives concerned? The first derivative was yesterday's test. And we can test with the first derivative for absolute maxes and absolute mins. This one will not have a maximum value, right? It might have a relative maximum. That's what this would be. But no absolute, because this goes up forever, okay? On the whole thing. There will be an absolute minimum, though, guaranteed. It might be shared twice, too, same value. Or, who knows? Anyways, we'll see. There's the possibility of this shape. But relative mins are what we tend to look at anyways. Now, that's not even asked for, but I want to keep reviewing because you guys didn't ask me any questions about it yesterday. I want to make sure it's in the back of your mind. Find the intervals on which this function is concave, up or down. We saw if it's a W, we could have possibly 2 regions possible in any inflection points. So, as soon as you hear concavity and inflection points, second derivative. Let's go for it. You do it once, and you do it again. And I'm going to assume we can do this because Riz is at this, except for that, that's 100. Second derivative. Actually, I'm more likely to make a mistake than you, because when I'm at the board, I really can't. It's like having your paper at your nose, and I can't even see. When I see 12x squared, I can't see the minus 108 very well. Like I make a lot of mistakes at the board that I don't. Anyways, to find inflection points, what are we looking for? Where it doesn't exist or where it's 0, right? Well, you can see that it's a polynomial. There's no division in it, no square roots. It's going to exist everywhere. But we do, so looking for these points, I'm going to set this equal to 0. I want you to explicitly write that down too. And then I'm going to factor this side. Want to wait. That's 9. Okay. Hey, this is perfect. Because I could factor some more, can I? Yeah. I'm excited. You guys tell me what it is. Live to factor another day. And more, you know this one? Yeah, good answer, good answer. Okay, so -3 and +3 are my zeros. They're the possible inflection points. So, to analyze zeros, etc., I'm going to do one of the old lines. And I'm not going to pull a full number line on here, sign analysis here. I'm going to just put -3 and +3 on it. That's all I need. Give it a little space here. I'm going to list my second derivative factors, eh? So I got +12. I'm going to put that down there. Now, positive 12 doesn't change anything. But if it was negative 3 that you'd factored out, sometimes people forget. So if it was, and it is negative 3, if this was like negative 12, let's say, and I'd put negative signs in here to remember all of those zones flip. But that's not the case here. That's a good habit to get into, even if you have a constant. All we're looking for is the signs. Now, x minus 3 is a 0 at 3. It's positive. Yep, 4 minus 3 is positive. And it's negative in these other zones. X plus 3, 0. Anything higher than negative 3, like negative 2, positive. Then, I say, the 12, always positive. I forgot to do that first. Abad, you really need to sleep. Or wake up. Okay. So there we are. We have two zones where it's concave up then, right? Concave up. I'll make a mistake right here. I'm going to say negative infinity to negative 3 in union with 3 to positive infinity. Right? Lessons. Since, what's the reason why I can state this?
Second derivative is greater.
Yeah. Since the second derivative is positive, it's greater than 0. Seems redundant, but the sign analysis alone will not tell me, or will not be enough for full marks. It tells you what to write in the statement. Concave down on negative 3 to 3. Since it's and so Ava's hand waving W seems appropriate because concave up. I don't know how high this goes. This doesn't tell me that. Then probably concave down and then concave up. Now, it may go down a heck of a long way on one and not the other, right? But this is the general W shape that you get, W. Coordinates of any inflection points. Where would the inflection points be? Just taking a look at my blue sketch, just like the other day with increasing, decreasing, I like to put arrows in there. I do this because this tells me it switches from concave up to down. It switches from positive to negative or negative to positive at 3 and minus 3. These don't have like max and min. They don't have a special thing. As long as it switches signs, it doesn't matter. It's an inflection. Sometimes you will get zeros where they don't switch signs. For example, if you take y equals x to the 4, and you take its second derivative, you'll have a 0 at 0, but x to the 4 just looks like a big fat wide parabola kind of U shape. It doesn't actually switch signs. But this one does. So B, it switches signs, so the coordinates of the inflection points are 3, comma. All right, we put it into, where do we put it in to find the inflection points? The original, good. Now, I don't know how nifty you guys are with numbers. 3 times 3 times 3 times 3, so 9 times 9, 81. Yep, 81 minus 54 times 9. You can use a calculator. Quick. Into the original function. Yeah. So where that would fall. Because if you put it into the second derivative, you're going to get 0 if you've done math. Let's say minus 54 here, you guys. 333? Or what do you guys get? Yeah, okay.
So I got two.
What do you get?
Negative 4.
Negative 405, okay, good, because I couldn't do that in my head. Negative 405 in both cases, don't we?
Yeah.
Yeah.
Oh, yeah.
Because the negative
Yeah.
3 squared, right? So, do you notice, there we are, okay. So inflection points imply that you have both x and y. That's where I put those red dots there. Right here and here. Now, I didn't graph this. This is just a rough sketch just so you understand the meaning of it, okay? Now, there's something called the second derivative test. We don't use it all that often because often when you're doing a first derivative test, it's pretty simple when you've already got it figured out. But there's some situations where you might. Suppose that the function f is continuous and it's on some interval that contains the number, pardon me, c. It's 5, 2, whatever. Pardon me. Now, if the first derivative gives you a 0, we know that's a possible max or min. So the first derivative gives you a 0, and the second derivative is negative. Right? Hey, negative. Which way, happy or sad? Sad. We've got a maximum. So basically, this is just confirming this. If the first derivative gives you a 0, possible max or min point, and the second derivative is positive, then we've got a happy face, we've got a minimum, right? That's what this is telling us. Find the critical numbers, give the points of the relative extrema. So we're going back to the first derivative, which we already have. I'm going to just copy this. You guys can see it all. You don't need to do this. I'm just... So, to find the critical numbers, we've got to set the first derivative equal to 0, right? And 0 equals, well, I'm going to factor out a 4 and an x. So x squared minus, is that 27? Is it? You guys, come on.
Yes, it is.
Yes, it is. Okay. Now, this isn't a nice one. Can you factor this? Yes, with the radicals, right? Because it's not 25. It'd be so nice if it was. But anyway. X minus the square root of 27, x plus the square root of 27. Square root of 27, can you break that down? It's what square times what? I'll write it down, and I won't do it in one step, okay. Think it through. And we know the square root of 27 is a little over 5, right? But it's 9 times 3 for 27. So you could say 3 root 3 is another way of saying the thing. Same thing. Blah, blah, blah.
What is,
Yep.
what is that?
This and this are the same expression because if you apply the difference of squares,
Yeah.
right, you get x squared minus 27, and we multiply out this, right?
What are we talking?
The zeros for the first derivative, because those are our critical numbers. Even if they are 5 point something or other, they're still zeros. They're possibly where the maxes and mins are.
Yeah.
All right. Okay, so we've got 3 zeros here. We'll do a quick sign analysis. Now, I'll do a quick sign analysis because I said I would. Now, it's actually easier to think of it as root 27 than 3 root 3, but if you're looking up answers in the back of the book, I'm sure they'll have 3 root 3 and negative 3 root 3, right? So I'm going to put down negative 27. No, I'll put down 3 root 3. We're getting better at this. Zero's in the middle. 3 root 3. My actual first derivative factors are 4x, x minus root 27, x plus root 27. I get a 0 for the 4x line at 0. Anything to the left will be negative, all to the right. X minus root 27. I get a, I guess, a 0 here. I have a mismatch, but it's the same number. Root 27, 3 root 3, same number. Anything higher? Positive, negative. Likewise, 0 here. Take into account the 3 factors. I see that I get a zone of negativity. So that means decreasing, increasing, decreasing, increasing. Just to remind me what this all means, as its first derivative, down, up, down, up. That quickly tells me where my maxes and things are. And we know the curviness of this from the previous one, right? We could connect this together and have a pretty good sketch of the graph, but that's for a later section. Anyways, give the points to the relative extreme of them. We know where the maxes, relative max and relative mins, plural for mins, are. We've got to use the original function though. This is why I like to think of it as root 27, not 3 root 3. Because to find the actual coordinates of the mins, negative 3 root 3, positive 3 root 3, it's easier to use root 27. So let's get this. The max mins, relative mins, I guess. Relative min values. Coordinates, the points, yeah, we do. So in order to do this, I'm going to write this one up. I'm going to use f of, and I'm going to use the negative root 27, only because it's easier for me to think of this one when I square it. You can use 3 root 3, it's the same number. And I go back up, x to the 4 minus 54x squared. I'm going to just write this out this time. I've already forgotten this at one point. Yeah, it is. No, it's 54. Yeah, I did forget. 54. 27 squared. What?
Is it not squared?
Yes, I got to the power of 4, isn't it? Yeah. Is that what you're asking me about? I made a mistake? Thank you. And it's a negative in here. Not that that'll change. This is so messy I can't even read my own.
Negatives for 27?
It's the negative 20. I'm going to plug in negative root 27 first. Yeah. But it comes out positive whether you use positive or negative. Should be the same answer. You guys tell me. Negative 27. I'll trust your answers. Maybe I won't. 81 times 9 is 810. Minus 81. What is it? Just for the start, right?
No.
For the whole thing? Well, I'm going to use a calculator and I'll see. That's what I keep Big Mama around for. She's a beast.
I got negative 7.9.
Why am I doing this if you guys get negative 720? Absolutely. I can see that too. I don't have to use a calculator. I'm just thinking here. I know that this is like 720, negative 720. Well, I can see this. If I to the power of 4, when I square the root, it's 27 squared, then, right? You guys, if I had to do this arithmetic wise, you guys don't, but I'm getting old and might go senile if I don't do this kind of arithmetic. Okay? Do you guys recognize 54 as 2 times 27? Here's how I'm doing it in my head. And then this squared is 27, right? So when I see this, I see a common, no. I'm thinking ahead, though. I wrote it down. That's what I was thinking. So I see 27 squared. 1 minus 2, which is negative, right? And 27 squared is 729.
Oh,
Right. So this works. Yeah. Anyways, you don't have to do it.
yeah. Oh, okay, good.
You have calculators. Just thinking, yeah, as you said it made total sense. That's what went through my head, among other things. Patent for, I won't even tell you guys. Anyways, so my relative mins are at negative 327, comma negative 729. And positive root 27, or 3 root 3 if you wish, 729. If you did a second derivative test and plug those in, they come out negative. Relative max is at 0, comma, I think you can see this one is 0,
Oh,
on the original function, right?
okay.
X 0 to the 4 minus 54 times 0 squared. Okay. This is sort of a review of some other stuff. Now, I'm not going to actually use the second derivative test to see if those were maxes or mins, because I could see from my sign analysis with the blue sticks, right? Now this is, so what can be said if all you know at 3 is that the second derivative is positive? What can we be sure about?
It's concave.
It's concave. That's about it. So this is concave up. It could be a number of ways to be concave up, though, right? So at this point, it could be concave up and increasing. It could be concave up and decreasing. We don't know that, but we know it's concave up. That's all we know.
And the minimum.
I'm sorry, what's that?
And the minimum?
We have no idea if it's a max or min there, though, at 3. Because all we're told is that just some zone, we don't have any further information. Now this is, if we're just told about this, we're just sure that it's concave down. Now this is where we have a culmination of things. If we're told in C that f prime of 3, so the derivative evaluated at 3 is greater than 0, so it's positive. What does a positive first derivative mean? Tells you increasing or decreasing, which one? Increasing. So for C, I'm going to do a little sketch work here. So for C, we know that at 3 it's increasing, and the second derivative is concave up. So this shape I could do a little better than that, right? It's going to be that shape, right? Because the second derivative tells us concave up, and it's increasing there. Do you guys follow me? This is sort of what I'm thinking of there. I don't know where, like it could be at 5, it could be at negative 12, but it's going to have that shape. Do you guys all follow me on this? That's sort of what I'm looking at. It's not necessarily, it's not a max or min. What about D though? Once you have 0, you know it's possibly a maximum or minimum, right, for the first derivative. But if it's concave down, what does this tell us here for D? So we've got So first thing is that it's either this or this. We don't know which one until we consider the second derivative. Which one isn't for D?
Concave.
It's concave up because it's positive. So we have a minimum at f of 3. So we could say about that point 3 comma f of 3. It's going to look like this. This is how specific we can get. Now,
Wait,
Mhm.
with the derivative, it doesn't change the graph.
with the derivative, it doesn't change. Okay, I'm not sure what you mean.
Like, the original equation says like x squared.
Okay?
The derivative doesn't change the graph, it's still.
Right, it just
looks like
describes.
X squared, but so using the derivative is just describing what's already on.
Yes, the derivative is describing. And if you think of this as the quadratic with the vertex at 3, right?
Yeah.
3 comma 0. This would describe the minimum at right at where the vertex is. And actually, by the time you get to the second derivative, it's a line, like it's a constant function, right?
Yeah.
So, is that clear?
Yeah, it's still kind of a little bit confused, like.
Okay, yeah. Why did I draw it downward? Thank you. Because you said minimum, but I was actually thinking maximum. I don't know, I just agree with you for no reason at all. Because when it's less than...
Oh, yeah.
Thank you. It's a maximum. Nobody else said anything. Okay. If you guys are sleepy in this first period in the morning, that's what I think it is. Bet you in 2 hours, Mac, you won't shut up, right? Eh? You just talk. And you're all tired. Okay. Think about this one here. The derivative is a 0, maybe a max or min, possible. But f of 3, f double prime of 3 is 0 as well.
So we're gonna just be there.
You don't know much. Think of a number of... Don't know much. Is really what I'm going to say. Not sure. Because I can think of a few scenarios. Look at this one. If at 3, if this was my function, and this is 3 right here where I put the dot, would this have a derivative of 0? Sure it would.
Yeah.
Yeah. So this is like x cubed minus 3. If I graph that and then pushed it up, plus 5 or something. And it switches signs for concavity. It could be the other way around too. It could be something like this. Those are both we're not sure what the heck it is. But it could be a scenario like that.